This is an overview of atmospheric chemistry for some of the major greenhouse gases. Earth's atmosphere is comprised of 78% nitrogen, 21% oxygen, less than 1% argon, and a very small fraction of several trace gases. However, it is within these trace gases where we find some of the major culprits of global warming, the greenhouse gases. Carbon dioxide occupies the largest fraction of the trace gases, followed by neon, ozone, helium, methane, krypton, hydrogen, and nitrous oxide. Some of these are greenhouse gases because they trap heat from the sun that reflects off Earth's surface. Greenhouse gases are not inherently bad, they keep the Earth warm. However, as we're currently seeing, too much of them can accelerate Earth's warming past the point of sustainability. These are some of the major greenhouse gases: carbon dioxide, methane, ozone, nitrous oxide, CFCs, HCFCs, and sulfur hexafluoride. For this presentation, we're going to focus on these four that are present as trace gases in the atmosphere already. First, let's talk about carbon dioxide. CO2 is the major greenhouse gas for a number of reasons. CO2 is present in far higher concentrations than the other greenhouse gases, although technically water vapor is more abundant. We don't really count it in the same way though. On average, water vapor stays in the atmosphere for only 10 days, while large amounts of CO2 can remain for hundreds of years. This is especially concerning because CO2 concentrations are most affected by human activity. We emit CO2 by burning fossil fuels and prevent its sequestration by clearing forests. When we discuss how to mitigate climate change, reducing CO2 emissions is the main focus by far. So how does CO2 leave the atmosphere? Well, unlike the other greenhouse gases, CO2 is not removed from the atmosphere by chemical processes. In fact, it's practically inert. Instead, CO2 cycles through the Earth as part of the carbon cycle. Several reactions in the carbon cycle are crucial to life. One such reaction is photosynthesis, where plants and photosynthetic algae use CO2 and water to produce carbohydrates for energy and oxygen. CO2 is also sequestered in the ocean by reacting with water to form carbonic acid. Increases in global CO2 levels have contributed to ocean acidification by this reaction, which hugely disrupts ocean life and ecosystems. Next, let's discuss methane. Methane is a primary component of natural gas, a widely used fuel source. The energy and agriculture industries are responsible for a large portion of methane emissions from human activity. According to the International Panel on Climate Change, methane is 34 times more potent in trapping heat than CO2. We still place more emphasis on CO2 when discussing greenhouse gases, but we cannot dismiss the potency of methane, especially considering it is the next most abundant greenhouse gas. Let's see how methane is chemically removed from the atmosphere. The major governing reaction for chemical loss of methane is with the hydroxyl radical. This radical is formed when water vapor decomposes in sunlight to form hydrogen and hydroxyl ions. The hydroxyl radical is part of a large number of atmospheric reactions. It reacts with methane by this reaction, forming a methyl group and water. Now let's talk about ozone. Ozone is a critical atmospheric gas because it protects the Earth from harmful ultraviolet rays. Its concentration is kept in equilibrium by these reactions. The dioxygen molecule is broken down by light into individual atoms. Then, those atoms react with more oxygen molecules to form ozone. Ozone itself decomposes in light back into the dioxygen molecule and an oxygen atom. Thus, the amount of ozone in the atmosphere should stay fairly constant. However, in the 1970s, scientists observed a hole in the ozone layer above Antarctica, allowing stronger sun rays to increase the rate of Antarctic ice loss. Further research showed that ozone decomposes by a series of reactions involving chlorine that is present in the atmosphere from the decomposition of chlorofluorocarbons. Chlorine breaks down ozone into oxygen and chlorine monoxide, which itself reacts with oxygen atoms to separate back into chlorine gas and the dioxygen molecule. The net result of these reactions is that ozone combines with individual oxygen atoms to decompose into oxygen molecules. This reaction motivated the recognition of CFCs as harmful pollutants and has led to a decline in their use today. Finally, let's discuss nitrous oxide. N2O is naturally present in the atmosphere and is a major component of the nitrogen cycle. However, anthropogenic emissions come from industrial and agricultural processes, especially from fertilizer use, as well as burning fossil fuels and solid waste. The EPA says it's 300 times more potent than CO2. Let's look at its atmospheric reactions. Nitrous oxide is an unreactive gas. Its main sinks are through photodissociation and reactions with oxygen atoms. N2O breaks down into its components in the stratosphere. One of the biggest dangers associated with N2O emissions is how it affects the ozone layer. In fact, nitrous oxides have comparable effects to CFCs and HCFCs in how they destroy ozone molecules, and today nitrous oxide is one of the biggest threats to the ozone layer. This is an example of a reaction where nitrogen dioxide decomposes ozone. So what does this all mean for the Earth's climate? We are currently trending towards a dramatic shift in global temperatures, and without reductions in greenhouse gas emissions, our current way of life will be unsustainable. Perhaps with a better understanding of atmospheric chemistry, we can realize how our actions affect the Earth, and we will be motivated to do something about it.